Most standard generative AI models operate as stateless functions. You provide a prompt, and the system maps that input to a static text output. Once the text is generated, the interaction ends. Agentic AI operates differently. These systems are designed as autonomous entities that actively perceive their environment, reason about it, and execute actions to alter it over time. To build an autonomous agent, the large language model must function as a cognitive controller, driving continuous behavior through its environment. This diagram illustrates the mathematical framework behind that behavior, a partially observable Markov decision process, or POMDP. It defines a continuous control loop moving through discrete time steps. The system operates within a state space. Because the agent can never see the entire environment at once, it relies on partial observability, extracting only the state data it can currently access. At every individual time step, the agent navigates this environment at executing a cycle of 4 linked functions. This taxonomy breaks down those core functions: perception to gather data, memory to store it, planning to determine the next move, and action to execute it. This persistent architecture provides the structure required to move from isolated queries toward workflows that interact with an environment over long time horizons. To understand how this POMDP loop operates, we have to look at the unified systems architecture, starting with how the agent interfaces with the external world. The perception function is responsible for extracting a partial observation from the environment at each specific time step. Early models relied entirely on parsing text. Modern perception modules use multimodal inputs, reading raw user interface coordinates, processing document object models, and analyzing continuous video streams to ground themselves. Once an observation is made, the system uses a memory update mechanism to maintain a mutable internal state. Relying solely on the model's short-term context window quickly leads to token exhaustion. Modern architectures solve this using explicit retention policies, paging out older data to long-term vector databases, and retrieving it only when strictly relevant. The update mechanism calculates the new memory state by combining the latest environmental observation, the agent's previous reasoning trace, and the immediate feedback from its last executed action. These active retention policies prevent the language model from collapsing under its own context limits, allowing it to maintain coherence over thousands of execution steps. Inside the central agent brain, the system moves to the planning phase. Here, it generates a latent reasoning trace before committing to any external action. Early agents utilized a linear pattern known as REACT, interleaving one thought and one action in a sequential loop. This approach suffers from extreme myopia. A single logical error propagates downstream, corrupting the entire sequence and causing the agent to stall. To counter this, architectures introduced explicit search mechanisms like tree of thoughts. Instead of a single chain, the agent treats intermediate thoughts as search nodes, exploring multiple alternative paths in parallel. This branching allows the agent to backtrack when a path fails. However, evaluating multiple hypothetical trajectories causes the required token compute and the resulting latency to grow exponentially. Frontier reasoning models now internalize this search process. Using a configurable compute budget at inference time, they evaluate these trees internally before outputting a finalized plan. Generating a plan is only the first step. The architecture also requires an explicit reflection mechanism. Reflection modules take sparse success or failure signals from the environment and convert them into natural language critiques. The agent stores these critiques in a verbal reinforcement buffer to explicitly condition and correct its next attempt. Without these dual layers of multipath search and self-correction, probabilistic language models inevitably drift into unrecoverable infinite loops when faced with complex obstacles. The final stage of the loop is the action policy. This is the mechanism that maps the agent's internal reasoning trace to an executable tool, physically altering the external environment. Initial action spaces were limited to brittle, predefined API calls. The agent's output was strictly constrained by required JSON schemas, severely limiting the scope of what it could accomplish. The architecture has since shifted towards executing code as action. The agent writes and executes its own Python scripts, allowing for dynamic control flow and the creation of reusable skill libraries. The current frontier removes these programmatic boundaries through native computer use and agent-computer interfaces, allowing agents to bypass APIs entirely. In this mode, the agent interprets raw desktop screenshots and translates its intent into low-level coordinates for mouse clicks and keyboard strokes. This expanded action space introduces a severe risk: hallucination in action. When an agent operates within a sandboxed API, a logical hallucination simply returns an error code. When an agent has unconstrained access to a desktop operating system, that same hallucination can result in the deletion of a production database. Even with advanced reflection and tool use, a single agent is constrained by its context window and reasoning capacity. Hitting this hard ceiling requires distributing the cognitive load. Multi-agent swarms rely entirely on communication topology. A mesh topology allows decentralized interaction, where agents engage in adversarial debate to converge on accurate solutions. A chain topology assigns strict roles, forcing sequential handoffs. A start topology uses centralized control, routing subtasks to specialized workers. As these systems scale for enterprise use, developers are abandoning open-ended chat loops in favor of flow engineering, defining the exact nodes and permissible edges of an explicit workflow graph. By modeling the workflow as a state machine, the system limits agent autonomy. Guard nodes and human approval steps dictate exactly when an agent is allowed to execute a tool or transition to a new state. Consistent reliability is achieved not by simply deploying a smarter base model, but by constraining probabilistic Bayesianing inside a deterministic, debuggable control graph. This chart evaluates these architectures using the classic framework, benchmarking them across cost, latency, accuracy, security, and stability. Comparing a standard language model against a hierarchical agent reveals a stark efficiency-intelligence trade-off. While the hierarchical agent achieves significantly greater reasoning depth and tool proficiency, that capability requires multiple concurrent inference calls, resulting in a severe penalty to both cost and response latency. Furthermore, deploying these agents in real environments exposes a critical security vulnerability. Because agents ingest untrusted content from the web and actively execute code based on that data, malicious instructions embedded in a web page can override the agent's objective, turning it into a confused deputy. The capability to autonomously execute complex workflows already exists. Deploying it safely requires treating the AI not as an infallible oracle, but as a probabilistic engine that must be enclosed in rigorous, deterministic governance.